This section is learning about the basic characteristics for mechanical waves. These types of waves require a medium for them to travel. That just means some sort of material. And there are two different types. The first type of mechanical wave is transverse, and that's where the medium or the material moves perpendicular to the direction the wave travels. You're probably most familiar with this kind, so you want to think about that up and down or side to side motion of a wave. So the displacement, the actual medium, is moving in one direction, and then the velocity is traveling perpendicular to that. You can think of transverse starting with a T, and then the sign for perpendicular is an upside down T. So you can remember that those go together. The second type is a longitudinal wave, and for this one, the medium now moves parallel to the direction that the wave travels. So if you think about having maybe a pool of material and then pushing forward, you kind of get that ripple effect. That would be more of a longitudinal wave. Or if you look at a slinky and you were to push a slinky, you kind of get some of the coils squished together and then some of them a little bit more spread out. So the ones that are squished together are pushing forward, and then the actual direction of the wave is pushing forward as well. So those are parallel to each other. You can remember this kind because longitudinal starts with an L, and then the symbol for parallel looks like two little L's put together. So this picture just shows you more examples, especially using a slinky. We'll probably refer to that example quite a bit. So longitudinal waves, the energy or the medium is going to be in the same direction, and then the energy and the medium are perpendicular to each other for a transverse wave. So now we're going to have just some basic vocabulary. A pulse would be one single disturbance that travels through a medium. So if you snap your wrist once on a slinky, then you've sent a pulse down. Or if you are trying to make water waves and you just push in that water one time, that creates a pulse. A wave train is going to be a series of pulses at regular intervals. So if you've ever gone to a sporting event and you see fans do the wave, if the wave makes it around once, that would be a pulse. But if they're really enthusiastic fans and the wave keeps going around and around and around the stadium, then that would be a wave train. Next, we have frequency. It can either be a lowercase f, or you might see the Greek letter nu, which is kind of a funny looking V. The definition for frequency is the number of complete oscillations or cycles per second. So if you see anything and then it's followed by per second, that's going to indicate a frequency. So you probably saw that a little bit with our rotational motion, like revolutions per second. An important thing to note about frequency is it is measured at a fixed location, and a wave train is needed. Since you're counting the number of pulses or cycles or oscillations, you need to have more than one. So you have to have a wave train in order to measure frequency. You can think of frequency as the number of wave pulses to pass a given point in a certain amount of time, and for us that time should be a second. I don't have a formula for you for frequency because it is used in other formulas. However, you need to note the units. Since it's the number of something per second, we're just going to put a 1 as a placeholder for the number, and then you divide by seconds. Another way to write that as an inverse second would be seconds to the -1, and this is called a hertz. So Hz is their abbreviation for that. Next, we have the period, which we've studied before. It is a capital T, and it would be the shortest time interval for the motion to repeat itself. We can also think about the shortest time for an object to move in one complete cycle. In terms of wave motion, the period would be the time required for a single wave pulse to pass a given point. And if you'll notice, it is the inverse of frequency like we've had before, and it'll be measured in seconds. Next, we're going to be labeling parts of a wave. So first, we have the wavelength, and its symbol is the Greek letter lambda. If you're writing it yourself, you may draw it like this, and then have this other leg come down. It's kind of like an upside down Y with a hook, or I've seen some people say, oh look, it's a two-legged giraffe, so you can remember the giraffe as the wavelength. The wavelength is the smallest distance between 2 points where a wave pattern repeats itself, and you will see a wavelength measured in meters. So if we look at a transverse wave, okay, so we've got some motion repeating, the wavelength would be from the top of the wave straight across until that motion repeats, which would be another top portion of the wave. So if you'll notice the wavelength, I have it measured from the top to the top of the wave. I could also place it down at the bottom portion of the wave or anywhere in between. So as long as I follow the wave motion, that wavelength will always stay the same. So it's the shortest distance for the motion to repeat itself. Next, we have the amplitude. It also is a type of distance that will be measured in meters. For amplitude, if we look again at our transverse wave, it's going to be the point of maximum displacement from the equilibrium position. And this equilibrium position is what goes through the middle of the wave, and that's typically going to be our zero location. You can have a positive or negative amplitude, but a lot of the times we're only interested in the magnitude, so you won't have to worry so much about those signs. The amplitude of a wave is determined by its energy. If you provide more energy, then you're going to have a higher amplitude. If there's less energy, there's a lower amplitude. And then next we have the crest and the trough. So the crest is the high point and the trough is the low point. So you want to think about where the amplitude is. If it's above the equilibrium line, it's a crest. And if that amplitude is below an equilibrium line, that maximum point will be the trough. And lastly, we have velocity. I'm going to go ahead and put speed of a wave because you probably won't see a direction indicated very often. So we can do the scalar or the vector version of this. It is similar to distance over time or displacement over time, but specifically our distance or displacement will be referring to the wavelength and the time will be the period. And remember, since period and frequency are inversely related, we can also substitute in for the period and write the speed of a wave in terms of the frequency and the wavelength. Either way, it's going to be meters per second. And remember that frequency and wavelength are going to be inverses of each other. So if one increases, the other decreases. So this is just another slide to review the velocity or speed of a wave. It can be wavelength over period or frequency times wavelength. So I have an example problem for you. My favorite radio station is Jack FM, so I picked that one to be our frequency. Sound travels at 3 × 10⁸ meters per second, and we are looking for the wavelength of this particular radio station. So I've labeled all of my quantities. Whenever you have an FM station, you'll see that the frequency will be measured in megahertz. You do need to change that and convert to hertz. And I know this isn't correct scientific notation, but a shortcut to converting is I would replace the prefix value with the power of 10 value. So it's 100.3 × 10⁶ hertz. Now we just simply plug in and solve. You should come up with about 2.99 meters for this particular radio station. As a side note, I did mention that FM stations are going to be mega. AM stations you'll see as kilohertz. So don't forget to look for those prefixes. You do need to convert to the base unit of hertz for any of your frequency values. So I have one more example problem for you. We have a wave traveling along a rope. It is observed to complete 40 vibrations in 30 seconds. So we have an oscillator, which is a machine that's going to move that wave up and down, and it can make it move 40 times in 30 seconds. We also are able to see that one of those pulses would travel 425 centimeters down the rope, and it would take 10 seconds to do that. We are interested in the wavelength. So I'm going to walk you through the steps. We know what the frequency is. We have 40 vibrations or cycles in 30 seconds. So if we plug those numbers in, and sorry about that little line there, this was my cursor that I forgot to remove when I screenshotted. So we end up with a frequency value of 1.33 hertz. Next, we have enough information to find the speed of our wave. I know we talked about wavelength over period, but remember that the speed of something can be any distance over time, so we're going to use those two numbers to find our speed. So we have 425 centimeters, don't forget to convert that to meters, and a time of 10 seconds. So this gives us a speed of that pulse or wave as 0.425 meters per second. Now that we know the frequency and the speed, we can use those two things to calculate our wavelength. And you should get a value of about 0.32 meters. So I have a few quick review questions for you. We're going to do 7 of these. For our first 2 questions, you are given this diagram. So take a moment and see if you can answer and figure out where the wavelength and the amplitude are labeled for each of these. You should have seen that the wavelength is labeled by letter A and the amplitude is labeled by letter D. Next, we have another picture, and you are asked to figure out which pair given of those letters will represent a wavelength. So typically you probably went from B to F because it's from crest to crest. However, that's not one of our choices. So we want to go through and examine out of the choices that are given, A to C, that's not one. That's actually half of a wavelength. B to D, same thing. That's only half of a wavelength. It's crest to trough, not all the way back to crest again. A all the way over to G, that's a little too long. That's about 1.5 wavelengths. So that leaves C to G. So the wave is on its way down at the equilibrium line, and then that motion doesn't repeat until we get over here. So this makes D our answer. For number 4, you are simply asked to find the frequency of the rotation of a second hand on a clock. So we know that that makes 1 cycle in 60 seconds for frequency, and that would be choice A. So for these last 3 questions, pause the video and take a moment and see if you can answer these questions correctly, and then come back and check your answers. For this first one on number 5, you're given a period and you're asked to find the frequency. So remember that period and frequency are inverses of each other. So I would simply take 1 divided by the period that was given, and that would give us 0.2. And it's 1 over seconds, which is a hertz. So this would be choice A. For number 6, same thing, except now we're looking at the opposite. This time we're interested in the period, so we're going to do 1 over the frequency. If you divide 1 over 440 hertz, you should get about 0.00227 seconds. And then lastly, a reminder that frequency and period are inverses of each other. So if the frequency increases, that means the period will decrease. That's it for our basic characteristics of mechanical waves, and we will be doing some labs so you can get some hands-on experience and see these waves in motion for yourself in class. Thank you for watching.